Hi everyone. Today's session is more or less about AI optimization, and to give you a general overview, just to confirm again, you can all hear me, right? There will be a little bit of background noises, but I apologize again for that. But yeah, so if you can confirm it once, I can go ahead then.
Yeah, we can hear
Uh,
you good.
okay. Yeah. Thanks, Valerie. So yeah, the focus today is not just to like cover up like classic AI optimizations, which people usually do, but the focus was to just pick up one algorithm and get an idea about how algorithms, like there are n numbers of algorithm out there. So it's very important to like know how they are being used, how the mathematics is being used and being implemented in like real life research right now. A lot of time this linkage is forgotten. People don't pay attention to a lot of these kind of details. They just focus more on the modeling perspective, like having greatest of greatest architectures possible, and they do miss out on a lot of optimization and a little bit of those kind of scopes. Yeah. So it's very important to understand this. So in this workflow, Anish, can you go ahead? So basically, AdaSwarm is one of this optimization algorithm that came up, and it uses the concept of particle swarm optimization. So PSO, uh, which is uh, which is like a very famous algorithm. And just to tell you a brief about it, like it's more or less like getting the hang of a flock of birds. Very simply, if when a group of birds are flying around for migration purposes, etc., etc., they benefit from each other's experience. So basically, PSO shows power or strength in a teamwork or a group. Basically, you try to understand the experiences of each particle, and you try to use that experience to actually reach to the optimal state of the solution particularly. So to simply take another example, and to make it very easy, the formal definitions are in front of you on the slides, but to make it very easy, let's take example of Sharma ji ka beta, which is I'm sure you are, it's just an example. The author also used this example and I liked it because being from India we all can relate to it. So there's always that topper in your society where whom people will point out, your parents would point out that, see, that person is doing so well. So what they try to do is they try to induce a sense of competition in you so that you improve yourself, right? So particularly the here as well, the experience of that so-called topper in your society is being used by, like, parents are trying to manipulate you. I would like to say that, but yeah, still they try to induce that sense of competition in you so that you improve your personal best as well because of the global best that is there in the society. So particularly if I want to go more into the technicalities, now if one particle is doing very great, for example, so you, the other particle which you are, you'll also try to improve your performance based on the performance of that particle particularly. So it's just like a real life scenario, you being motivated by people around you, and you try to learn from experiences such like the community of god as well. You try to learn from each other and you try to improve your personal best. You will try to come up with good research papers by looking at other people's research, etc., etc., and we become a group, a flock of bird particularly. So this is what PSO is. We try to often find the global optimal solution, which is usually the biggest challenge of PSO as well. Because a lot of time when you are trying to solve any algorithm, optimize any algorithm, you tend to find a lot of near optimal solution, but not the perfect global optimal solution. So that's also a drawback, but there's a lot of power factors in this algorithm which you are going to realize soon. So this is like a very general overview about what it is, but on the slide deck you can actually see the formal definitions that is there. So yeah, Anish, can you just move to the next one? So now, see, PSO, this is like a very simple explanation. So, see, you will find a lot of articles online. You will find a lot of explanation. You'll find codes as well online. Particularly here, I've tried to break it down in a form of very like an algorithm, a very generalized layman overview of what it is. So here, as I had expressed, so it's very easy to understand, and that's why these algorithms like PSO are called evolutionary algorithms or genetic algorithms. These kind of algorithms, these are evolutionary algorithms. You can relate with real life things actually to understand these algorithms, and they are very intuitive in that way. So now here you start with every particle search for the optimum. Now you have to imagine that you have a search space and you like push out like n number of particles in that. Now each particle is trying to search for the optimum, the global optimum in that search space particularly. Now every particle moves. We have to keep in mind that the particle is moving. That means any particle which is moving has velocity, right? Now what happens is every particle remembers the personal best or the p best. So you want to, so your personal best would be like an IIT JEE rank of, I don't know, 1000, something like that. So that would be your P best. But your sadly that topper in your society might be having a AIT JEE rank of like, I don't know, 90 or 100, under 100, something of those sorts. So yeah, that's the global best kind of thing. So now what happens is particle in the swarm cooperate and exchange info. Sadly, in real life, this doesn't happen usually, but in algorithmic sense, they try to exchange information with each other through which they improve their results, particularly. Now, this co-op can be broken down, or the cooperation can be broken down as follows. So I guess just give me a minute. I'll just be shifting now to the laptop. I'll need a 2 minute break. Yeah.
Yeah. Hi everyone. I guess now you can also see me. So thank you, Anish. I'll just share my screen now. I'm back on my laptop. Yeah. Yeah, Balaji. I'll be covering that particularly. What particle means here. So I hope I'm all clear now. Like you can all hear me. So are you able to view my screen? Okay. Um, yeah, yeah. Okay.
Yes, we are.
Okay, okay. So yeah, so simple explanation of it. I was there on the cooperation. I'm sorry for again for the break, but yeah. So co-op can be broken down as follows, particularly. A particle has neighborhood associated with it. So see, these are all controllable parameters that you'll find. So like what is the neighborhood? Particularly can be n number of particles. Like you can define that. That's why it's an optimization. You will always have parameters to like tune. So number of what is the neighborhood? The particle is associated with. A particle knows the fitness of those in its neighborhood. So this is particularly the value that like what is the p best of the next particle. You know that, but that's why the cooperation is happening. And the this position is used to adjust the particle velocity. So you, what happens is your velocity is also being controlled through that external parameter or the global best particle particularly. So your success of getting a good rank, getting a good college is somewhat getting motivated from the fact that there is someone in your society who's doing very good and you are getting the examples of that person. So it's that kind of a cooperation. So you need to actually relate it to every aspect of your real life scenarios as well. And this each finally in each time stamp particle has to move its to its new location. So this new location, if you imagine a search space of hyperplane, you're working like you're moving around that space, you're trying to find those optimal solution, the global optimal kind of things. So your changes in the velocity are taking you towards like a particular position which might be the global optimal, which might be, as I'm saying. So it won't give you like, again as I said, it will give you the feasible solution, but it will not always give you the global optimal solution. So it's very important to understand that. Moving forward, so particle adjust their position according to psychosocial compromise. So again, the co-op which you saw earlier. So it's just an example. So this X particle, again, like there's a lot of repetitions there, but again, like I'm just trying to give you the perspective of the same story from different diagrams, different view, different kind of theory. They all point to the same thing. And again, I'll be going into the mathematics a bit of it, like a bit of mathematics behind this as well. But yeah, like this is just a movement towards like what AdaSwarm is later on. So yeah, so you are X, you are moving towards my best performance, your best performance, and the best performance of your neighbors is PG. So P global, P personal, PI is being referred to as a P best. So see, now you look at the movement. So your particle is changing movements through this. So particularly the directions are also changing. You were moving in a particular direction, you got a personal best, you start moving towards that, And then from your personal best, you start getting motivated towards your personal best of the neighbors. So what neighbors you define, for example, you define 10 particles. So those 10 particles particularly, whichever would be the best in that 10 particles, you are going to move towards that direction, so your velocity is getting controlled. And this is the kind of formula which summarizes the whole story that I've been talking about. So now, as I said, right, I'll be moving towards the mathematical aspect of it. So this is the mathematics. Like if I want to define the function, if you look closely, I'll like I would want you all to give it a look. So please take a minute as well to read through it. And yeah, I'll go forward with it. So you can have like 30 to 45 seconds at least to just go through it. What is written? Well, it's very important to understand as well these aspects, because I've given you the real context, but yeah, it's still like very necessary to know what is being written. Okay, yeah. So I assume like you must have gone through at least to the starting point of it. So very simple definition, like xi being referred to, xi being the position of the particle being referred to by like x and y coordinates. Then you have the velocity as well, which has been denoted with a vx and a vy direction. So particularly, we are going with the proper geometrical analysis of velocity. You must all be familiar with it. So yeah, like particularly now, if you see closely, your velocities are updated through the rule below. So now, if I go one by one, this C1 and C2 are like these parameters which you will tune. So R1 and R2 are random parameters. Again, these are randomized. So very important focus: R1, R2 are random parameters. C1 and C2 are controlled parameters. So there are two parameter, though two stochastic parameters here. If you look closely, C1 R1 and C2 R2. So these are like, this is what you tune to take your search to find the optimal solution in the search space. So there might again be a lot of confusion about what C1 is, R1 is, C2 is, R2 is. So you can make these parameters to be learnable. Now if I take it towards ML, you might want an algorithm to learn while optimizing as well. You might want to find, either you would like to like, so there can be two ways of approaching this PSO altogether: from a deterministic point of view or a stochastic point of view. Deterministic point of view can be where you'll stochastically try to, like, I would say, like, it's kind of a mix. But technically what you'll do is you'll run through n number of iterations and you'll try out different parameters and you'll try to see which is the best one, like hyperparameter tuning, very simple. Other ways, you might want to train the model with the optimizer in a way that you can identify what was the actual proper C1 R1 set, or the C2 R2 C1 R1 C2 R2 set in that particular like a setting or particular scenario where you were trying to train any model of yours. So it can be two ways: you can make it a learnable parameter, you can just iterate through it and find randomly, like stochastically completely, and through deterministically would, I would say, like through ML or those kind of aspects. So yeah, like so this is like a general outlook of how the algorithm, how the loops go about. So I have a quick demo. I have a quick PSO demo as well, because like, see, I said a lot of theory won't make sense because this is optimizations I'm talking about, and a lot of things are just mathematics. So it would be important to like show you a real life, just a very small code. It's a very basic code you might find online because it's a very basic example I've used. And just give me a minute. I'll share my screen to show it to you, and you'll see the code as well. So yeah, just give me a minute. Okay. It's up. Let me know if you can see my. Can you see my screen? Yeah, okay. So if you see closely, like I have used a very deterministic kind of a setup. Sorry. So C1, C2 are the hyperparameters of the algorithm, like 0.1, 0.8. I have been set. These are all empirically set. These are not like, they haven't been like, there's no approach by me through which I found these parameters, but rather it's just like empirical thing that is being used online for this particular function that I picked up, the objective functions. So this is the objective function of which you are trying to find the global minimum particularly. So if I run it, I hope I can show you the GIF. So this is like, it just shows you what was the PSO best solution, what was the global optimal actually. So it's running. So it also will save a GIF which shows you how the real life particles work. So this is actually the working code which will explain to you how the whole scenario is happening. So just give me a minute. So if you, it's going to be very fast because like the setting is such, the function is such. So if you see closely, can you see the particles are moving? Like obviously you can't see the interaction because it's going to be very fast, can't slow too much, but yeah, like this is how they're optimized, they are like converging to a global optimal. So solution, so they start from a search space of this and they reach up to the global optimal like this, particularly if you see, and nearby the global optimal, I should say, because from the algorithm results it gave you global optimal solution like minus 1.808, but the result would have been minus 1.80827, but it reached up to like 0.80835. So again, as I said, it will not always give you the global optimal, but somewhat near to it. So this is like a real life working of how the whole setup is working. Now I'll share this code later on, like if you want to go through this, a very simple function, like not a complex thing. So don't need to focus too much on the this part because it's just the plotting aspect. This is what is important for you all to look into, like how the updation is being happening. This is the use of those formulas that I used. So as I told you, right, R1, R2 are the random parameters, C1, C2 are kind of like hyperparameter of the algorithm. Sometimes people also use R1, R2 as the hyperparameters of the algorithm. So there can be a lot of variations to it. So you have to also keep that in mind because I can't cover all the variations. And this is a very simple baseline of this whole algorithm. So you might find better versions of it. You might find a lot of better codes, but a lot of functions that is it's optimizing and those kind of stuff. So it's just to give you an intuition and you can obviously explore it on your own later on as well. So yeah, like this is the coding aspect of it. Now I'll be back to my slide. Okay. So this slide particularly, again, like it all, this is like what are the variants in the market particularly. So there are a lot of variations of PSOC. Now I'll tell you one thing, a very important thing here is that such an algorithm, when you, I'm sorry. Yeah. So it's very important to remember that this PSO is has a very simple implementation. So you saw the formula. If, just to revise you, this is the formula that we are using. Simple formula, one liner. That's it. You have to keep in mind that due to the simplicity of this algorithm as such, there are a lot of variations, there are a lot of combinations of PSO. So here I will not, actually my focus is not to explain each variant, but rather give you a context about how PSO is there. So PSO has like a lot of versions. It has the hybrid of genetic algorithm and PSO, like GAPSO, which again, so it uses genetic algorithm. So I'm not sure if people are like, if I guess you can give me a raise of hand as well, because like who all know about genetic algorithms so that I can get an idea. Uh, yeah, I'll just, okay, so at least one of you know. But yeah, like again, going back to it, so I guess it would be a difficult topic to take up, but yeah, genetic algorithm is a very famous algorithm again for AI optimization. So you should go through it. So, the other one is an evolutionary programming with PSO. So you use a tournament selection to move. So particularly again a brief as the name suggests, it's a tournament selection. So it's kind of like a tournament happening, and you keep on selecting uh, uh, and like X number of particles from a particular set, and you each time compare and compare, and you finally find the the best possible solution or the best possible candidate. So it's like a tournament. You keep on having like one-on-one kind of competitions, and like you leave out stuff. So it's kind of that. Genetic algorithm is more or less like exchange of genes particularly. So you try to relate your algorithmic approach with gene combinations of human beings. So for example, if you have an X chromosome and a Y chromosome, for example, a very common. So if you exchange like a lot of things in between that, so that's kind of like how you understand genetic algorithm. There's an exchange of knowledge in that sense. So very important. So adaptive PCO, it uses random component to the inertia weight. So again, it applied fuzzy logic. Right now, what you saw, right? You saw me using like deterministic parameters. I used C1, C2 to be like zero point 0.1 and zero point 0.8 to be the weight of the inertia, this W here. But if you have an adaptive PSO version of it, you're going to apply a fuzzy logic. So particularly you apply fuzzy logic to determine those parameters. So again, a simple variation. So you can also come up with a lot of variations. I've found personally that people have experimented so much with PSO that even young authors, I've found young authors publishing papers on PSO with different variations actually. And this can be good approaches for if you want to go through such papers. I would suggest using like focusing on conferences like ICLR, ICML, triple AI, and NIPS kind of conferences. So they discuss a lot about these mathematical algorithms like ML, the core ML, AI optimizations, and those kind of stuff. So, and even reinforcement learning based conferences are very good for finding such things actually, because they do use a lot of your core AI. So again, so I wanted to give you a brief into this. And yeah, so multi-objective PSO, discrete PSO. In my workplace, we use a lot of multi-objectiveness and algorithms. So Pareto dominance Pareto is a concept, a very famous concept. So we use actually to determine in the robotics and robotic warehouse optimizations. So again, like there are various variations, and I'll, because it's not there like right now, I can't focus too many on a lot of topics. So yeah, like I'll skip it, but yeah, you can give it a look later on. So what are the advantages of PSO? Like if I come to real life scenario, it does not depend on the gradient of the objective function. That's very important. You are not using dy by dx here. You're not doing the gradient of the objective function. That's a very powerful thing, and that's why you have a discrete version of the PSO. It can solve a discrete problem, so you don't need to have it to be continuous. That's a big advantage. A lot of people might give me a counter arguments. There is a lot of discussions that can happen, but just want to give you an idea that it does not require the gradient. It can be easily parallelized. So people who are involved in optimization, it's very important for you all to understand that parallelizing your algorithm is like the biggest win possible right now with the power of GPUs, like millions of threads that you have in under your control. You just need to set up each particle on each thread, and you're good to go. You can have an immense search space, and you can distribute your particles over each thread, and you can like easily like parallelize it on what they call it, G or like GPUs, even CPUs, powerful CPUs. So yeah, that is a big win on the large scenarios on large scale. So you have to look at it from high performance computing perspective as well. Now the biggest disadvantage I've written, like especially like it does not give you like as I said, the optimal local searchability is weak. It always doesn't give you the global optimal. Even in my run that I showed you, it didn't give the exact optimal solution. It gave near about that optimal solution, which might be a lot of time a problem, because when you are talking about for example rocket science, the best example, you are talking about satellites, something, you can't sometimes have that kind of error in the margin of error. So yeah, that time it might not be useful. So it's very important. Now this was just about PSO. I've taken a lot of time what PSO is. Now, so you got a basic idea about what PSO is. So I'm also trying to imbibe the fact that I'm trying to provide you a picture about how you want to go about such papers. If you are talking about like papers in NIPS and AAA, ICL, ICML, it's very important to know the mathematics of the base concept. So you don't need, and the most important thing is you don't need to go to the depths of that subject. A lot of times I've seen people like they are afraid to try out or read a paper just because they say that I don't know the mathematics, it's too daunting for them. But it isn't. A PSO has a lot of explanations that you you can find like tons of books actually just written on this topic. But the level of explanation I gave you, like what PSO is, how you are just exchanging information, that's it for you. You can go ahead and start reading these papers. You'll make sense. It's not that they are so difficult that you actually need to do a thesis in PSO, like a particle swarm optimization, and then only you'll be able to make up. As I told you, right, you'll find a lot of young authors like fourth year students, masters, first year students, second year students publishing papers with PSO variations. So a thing to keep in mind. Now, uh, the paper that I talked about, like what I started with, AdaSwarm, what that is, you have three contribution in the paper. So a very important thing to understand a paper. Like what was the contribution? First, it discusses what EMPSO. It's a small variation of PSO only, which I discussed earlier. Then we have approximation of the gradient. So they have two theorems that they have derived or they have introduced. And then you have AdaSwarm, like the optimizer to use. You might want to use it. Like you have the Adam optimizer, Adam W optimizer. So this is also one of them. If you want to try it out, you can try it out with your uh, next training that you are going to do. Maybe today only or tomorrow, whenever you want to do it. So yeah, what is this EMPSO? So EMPSO has, I'll keep it very simple. It is exactly the same, but it has a factor. I'm sorry. So it has the factor of momentum. Now, momentum is you can see like the algorithm remains the same here. So the weighted portion of inertia, like earlier you had W written here, WVI. Now you have 1 minus beta, where beta is the momentum factor, and you have an extra element of B into MIT. Now, this MIT, as you can see, is the momentum of the particle. So, what usually momentum in AI optimization is used to steer you away from any stagnating local minima. So, they intelligently, it's a very simple introduction, to be honest, not a complex introduction to introduce in any algorithm. They introduced a this beta factor, which is a momentum factor, and they try to steer away from any stagnating local minima, which you can find in such particle optimization. The example that I showed you earlier, it was the you could even make from the graph you could make sense that it is actually the you'll be able to easily find the global minimum. There were not local minimas, a lot of local minimas there. So but when you're talking about real life scenarios, you'll be training like tons of parameters and a large huge hyperspace, sorry, search space. You might be facing this problem of stagnating in local minima. So this momentum factor removes that. So that's why this is like the EMPSO that is there for you, exponentially weighted particle form optimization. A simple introduction might be, and in the paper, if you start looking at it, you will find okay, what is this? Like it's a new version and all, but it's a very simple introduction as I showed you. Now it does the two part. Now how they have made you understand it, it has the exploration and it has the exploitation. So again, the words give away everything. Now, exploration is done by algorithm to search for other possible solutions apart from what you have right now. So it will try to help you find other solution, like other places where you can maybe a vicinity where you can find the good region. So exploration. Exploitation is when you try to find solution of higher precision, like you try to exploit your knowledge very well in a way that you now want to have the right answer. Like earlier you are trying to find the right region of answers, like you might be trying to find that area where it might be the answer might be. The exploitation is once you have found that area, how do you exploit the knowledge to get the best solution possible there in that region. So this is like the combination of exploration and exploitation. So this paper discusses that part only. So they are trying to use exploration and exploitation. Now if you see here, it's exactly same to what PSO's definition is, but here the VI has the extra factors of the empirical weighted momentum here. So EPSO didn't have that, they have it. So yeah, again, a simple thing, the same thing, but a little bit of changes, which is most of the time the story behind any PSO extension, usually in the research papers. So so see, this is very important now. So if you read through this, it just tells you that when you start the exploration phase, you start with the exponential weighted average tries to provide you like if you look at the algorithm, it will try to provide you like high velocities actually. So when you are doing exploration, your velocities tend to be a little higher. Why? Because you are trying to look into search space quite fast, like trying to find where is that location. So it's an accelerated time that you have. Now what happens is so when you try to accumulate with little time, as the time progresses, what happens is you trying to shift from the exploration phase to the exploitation phase. And when the exploitation phase starts coming up, uh, your your recent velocities tend to go down and down and down, particularly. And now what happens is, because you are trying to find an exploitation area, your velocities are going to go down so that you can look well into that area. So this is how this beta factor is helping you. So they try to increase the weight. So weight, in a sense, that also they try to shift your, like, decrease the velocity in the exploitation region and improve the weightage, particularly weightage of the solution you are trying to find in that particular space. So again, exploration, the weightage is not on the solution we are trying to find, but rather the velocity, because you want to focus on a large amount of area. But in the exploitation, you want to focus on the solution, but not on the velocity. So this is how this 1 minus beta factor helps you when you try to expand it and you try to solve it, particularly. So this is going to be very important to understand. What is the two theorems now? I know, like, it might be a lot of mathematics, and I can't go too much into the mathematics and provide you, like, what do you call, like, proper proofs and all. But yeah, like, the on the right, I have written a very simple definition of what it tells you. So what they're trying to do is they're trying to prove an equivalence between a gradient descent and vanilla PSO. Why it is important? It is important to approximate the gradients of differentiable function. They are trying to tell you that if I have a vanilla PSO and I have a gradient descent algorithm, then you can relate both the algorithms. You can prove them to be equivalent. That means you can interchange them each other. So you can use the approximation of a vanilla PSO almost equal to the gradient descent value, particularly. So you're trying to approximate. You're trying to just, so they try to prove it, particularly. So because, so that they can tell you that yes, they can use it on non-differentiable, like both differentiable cases as well as non-differentiable cases. Because, like, that's why the PSO is quite important. It's not always that you're going to find a search space which is like continuous, or like you might find discrete broken pieces and a lot of things like discontinuous algorithms as well. So it can handle those situations. Now, there's also an equivalence between SGD with momentum and the EMPSO. So see, PSO and GD, and then we have stochastic gradient descent with momentum and then EMPSO. So they are trying to prove those equivalence with the differentiable, the famous differentiable, optimizer, which can help you in finding solutions of the differentiable function. So they're trying to relate it with those kind of famous algorithms and trying to tell you that their solution is approximating it. It's almost at par with those solutions. So this is what they're trying to tell you through these two theorems. So one, they had an EMPSO which they proposed. Second, they have theorems to mathematically prove that this vanilla PSO, your EMPSO, can approximate the values just like GD and SGD, highlighting the fact that the performance is not getting worse. Actually, they are able to maintain the performances, which a lot of people. So I'm sure, like, I'm not sure who all are very familiar with this kind of algorithms, but they usually they suffer from very bad approximations usually. So a lot of time, any author, a famous author, or a person who has done PhD in the subject, they're going to question that why should I remove GD and SGD from my picture, just because I want to have it for like a non-discontinuous function or something like that. Because most of the time in real life scenario, you might not find those solutions, not find those scenarios particularly. So yeah, like, this is important. So that's why they had to, like, through the paper tell you that yes, we can correlate with it. And when you talk about using my like their algorithm, you won't suffer from like performance loss. So, and you have already told you, like, the big two advantages there, that it can handle like non-differentiable functions as well as it can be parallelized. So it's a big key, it's a big win. So
Guneet, sorry to interrupt. Like the way they are doing is because they just want to say that we can use EMPSO for differential functions as well. Like they are just creating,
see, yeah,
this thing
yeah,
for,
yeah,
you can just simply say that it's for non-differentiable and for differentiable as well. Like both of the
exactly.
words,
Yeah, yeah. So
right?
exactly. Thanks, Vinayak, on that. Exactly. Like it's they're trying to just justify the fact that even if we are proposing an algorithm which can handle non-differentiable cases far more better, it's not losing on the fact that it might not perform well in the differentiable functions, which is usually
Yeah.
the case in real life scenarios. So they're trying to
Hmm.
maintain that, and because it's a proper justification, you have to also think from a reviewer's perspective. If you are going to review a paper, you might say, right, why do I need a approximation if I can use a proper algorithm to give me the exact value, right? So there they have there this theorem, these two proposed theorems, these two proposed they have also given derivation in the paper, which is like rarely you ever find in good paper, in optimization papers. So this was considered to be one of the good papers there in the conference. So yeah, a very important thing. So these are the results if you see. So again, like I have put these results for your understanding. Like you can go through these results and try to see how well they are performing. So they have tried to show you like differentiable functions with GD versus PSO, then SGD versus EMPSO, and then the non-differentiable functions. So a lot of important focus can be put on like iterations as well, which is a very important aspect in optimizations, and also the values of like the global minimums, the SGD minimum, and the emulated GD. So you have to look at these results. It's very important. They have also proposed now. See, a very important thing while reading papers right now, what they have shown in in these tables are like the best results that they would have got. So if you go by their parameters of C1, C2, eta parameters, and the beta parameters, they have showed you cases where they are beating SGD and GD, but that might not always be the case. So you don't need to also blindly follow the results, and also but try to understand the intuition. These result table just simply tells you that okay, SGD and GD are nothing in front of PSO and EMPSO, but that's not the truth. So you have to also be very intelligent in that perspective while understanding any paper. So again, like just wanted to raise a point, because they have specified the parameters here. They are trying to highlight the power of their solution, but it's not necessary all the time. So again, while reading the papers, do keep these things in mind as well. Finally, I'm at AdaSwarm. I'll just use a simple definition, and these two EMPSO and the two theorems actually lead to the AdaSwarm. Now, what happens is an AdaSwarm, you have the atom optimization, but they replace the gradient here there in the atom optimization with the approximate gradient via their equivalence theorems. And now if you see closely, the replacement, say they replace the gradient calculation through their gradient calculations. Now the approximations they had, now they that approximation just summarizes that this is now their new optimizer. The thing that was calculating the differentiable functions, the gradient of differentiable function, have been removed. Now they have introduced their EMPSO now, which can solve this challenge. And now it has power of three things. It is easily it can differentiate, it can handle non like differentiable functions with same performance or proficiency, I should say, as an Adam optimizer. Secondly, they can handle non-differentiable functions as well. Now additional power. Third thing is it's easily parallelizable. Now they can parallelize it on GPU, and it would be way faster than any Adam optimization. So if Adam optimizer is taking like 10 iterations on a CPU, they might they might do it in one. So that's the power. They have the parallelizable power now. So these are the tables they are tried it on different data sets now. I still question, so it's very important to question the approach of the authors as well. I don't know why they use the data sets rather than algorithm. A lot of people ask me when I have talked about this algorithm a lot with a lot of people, and they raise the point that the author evaluations on data set was a kind of misleading aspect, because it doesn't tell you a lot of things. The best thing that it would have been if they would have used it in combination with algorithms, like for example BERT. If they had AdaSwarm and Adam, what were the results then? So it's an important aspect, and might be a future direction for this paper as well if someone is too motivated. I was also thinking like, what if this analysis was done from the perspective of algorithms instead of data sets? So I just won't go through the values, but yeah, they do perform very well actually. If you closely will look at the result table, you'll find that their algorithm was performing good. So yeah, again, a good thing to question. It's very important. By giving you a presentation, I'm questioning their approach as well. So I'm not saying I'll blindly follow their paper. It's very important to question the approaches. As again, as a researcher, you should do it. So yeah, like they have discussed the same thing, and they are using like differentiable loss function and non-differentiable loss function. So you have to look at that. So they have used these two combinations of how like differentiable loss function, non-differentiable. So again, very important. And the conclusion is very simple. Again, like conclusion is just the takeaways, how they used a very simple algorithm of PSO, how they smartly introduced a momentum factor to improve the PSO only, and then how intelligently they tried to approximate the differential functions value with their solution, along with adding the two powers of parallelizable and parallelization and what they call the approximation of non-differentiable sorry, calculating a non-differentiable function non-differentiable function loss value as well. So this is how they played it out. They got one of the best paper out there. So yeah, like this is how smartly you do research. So this is a very smart way of doing research, I would say. Like, so this is just a takeaway. There's no slide on it, but I would say like the smart takeaway from their approach as like overall approach was the fact that they took a very simple algorithm. They introduced very simple but intelligent changes. You as an AI researcher, obviously for young students like us, young people in research, we might find that okay, this is too like overwhelming or something like that, but it's not. If you have been in this field, it's not a big change that they introduce. And the best part of this paper, what I found personally, was the fact that how they knew that it would be really important to approximate with differentiable function. There they got the paper across particularly. If they would not have given that particular thing, and they would have just said that okay, I am going to propose an algorithm which is like which can handle non-differentiable functions, it can be generalized very easy, parallelized, and you are good to go. No, they would have literally failed there only. The approximation was the key. People don't focus on the approximation again because yeah, you're going to say why should I use that as one? I have SGD, I have item W, I have like different number of optimizers. So this is like a very key point. You whenever you're proposing a research, it's very important to actually think like a reviewer as well. Someone is going to question your research. Someone is going to ask you like, what are you going to answer to those reviewers? Are you do you have the right answers already? If you know the questions, you're going to answer them beforehand only, and your papers won't get rejected at all. So it's again a good takeaway. So it's very important to also look at researchers' writing style and understand the way they smartly get papers across to the community. So again, a good talent to have as well. So yeah, that was like a very, I would say, a very weird start to any AI optimization, but the right way of starting any AI optimization. Pick up a paper, look at the basic algorithms, just read a brief about it. Don't start digging around books and start solving problems or solving solutions or anything like that. Just pick it up, try to implement a very basic code like I showed you, just to see what is happening. Use that particular thing. That's just a 2 hours of activity. After 2 hours, you will be good to understand these tough papers. It was one of the tough paper, but through this strategy, I was able to break it down quite easily because I was very new when I read this paper. So yeah, like that would be my suggestion overall as a takeaway. So yeah, thank you.
Thanks, Guneet. It was a great uh, talk. I really enjoyed it.
Thank you. Thank you,
Okay,
Anand.
thanks a
Thank
lot,
you, guys.
Guneet. Yeah, very informative session.
Yeah.
And I think there are a few questions in the chat if you want to take them.
Yeah, I'll just give me a minute. Yeah. So, what if you finish at the particle? Um, Balaji, can you come on call? Like I would like to
Yeah,
discuss something.
sure.
Yeah. Yeah, you can ask me directly, right? Yeah.
Yeah. So
So you
what
said
if
what? Yeah. Yeah.
so
Go ahead.
what if the particle is in the global optimum itself? Can it? So for
So see.
example, yeah.
Mhm. Yeah. Yeah, go ahead. Go ahead. Sorry. Go ahead.
So I was just asking. So case of like
Mhm.
SGD when we use gradients for performing the optimization. We So when we are in a global optimum, we have the gradient to be 0, right?
Yeah.
So we don't move around. So what happens in the case of cortical?
That's Yeah, that's a good question. Particularly in the scenarios that I read through. I'm going to talk about from the paper's perspective now. In the PSO,
Okay.
see, the PSO, this can be a problem, right? Because what might happen is that you might be at that position, which is a very rare thing when you have a lot of complex functions, right? So you cannot hit. This is like a one in a billion chance kind of a thing, mostly most of the time,
Uh,
that you hit the global optimal directly. that's
mm,
that's rarest of the rarest situation most of the time.
yeah.
So but I would say the momentum factor in the EMPSO, if you try to
Mm,
calculate for such a scenario, like I'll have to find such a scenario, to be honest. So if it is there, then your exploration factor would go low instantly because of the mathematical formula. When you expand that mathematical formula, your exploitation factor would increase easily there only. Because what happened is, when you start the algorithm, you'll already be in that region of best
yeah.
possible solution,
Yes.
right? So your exploration won't be very high. Your exploitation would be high from the beginning then. So that's like the controllable parameters. What happens usually, your question was like very intelligent in the sense that what happens, I guess in PSO you might face a error, or like error in the sense that you might go beyond the range. This might be a problem in PSO, but not in EMPSO, if I'm not wrong. So it should not happen in EMPSO. But yeah, like it can be worth a trial. Like that's a good question to look at, like how many times such a situation occurs, because this is, I feel like this will be a very rare situation to happen. It can happen, but I don't think so it will happen frequently, like that it should cover. Like PSO should be like not considered at all. But yeah, it might be a shortcoming for it, but not for the EMPSO, because I know, because of the factor calculation, your exploitation would be already be high, like when you start, because of the result. Because right,
Mm,
you have to imagine you are updating the velocity. So if your velocity is in the region of global optimal, again, right, so
yeah.
it will not be increased like rapidly. So that's very important. But maybe it's a good question, I should look at it as well, like from my side. This is my intuition of the approach, but maybe there are different answers as well. I can look into that, we can discuss that. That's a good point,
Yeah.
yeah.
Okay. Thanks.
Yeah, no, yeah, no worries. Anything else, like any questions in general as well, if you have any?
I guess like Guneet, this AdaSwarm thing really created a new way for researchers to research upon, like merging deep learning with AdaSwarm and trying out, as you mentioned, like using BERT and try out on different data sets, like to see what results come out. Right, that's a new field of research area. That
See,
part was good.
yeah, that's the main motivation for me, like personally as well. Like discrete
Mhm.
optimization, like a lot of algorithms are never like converged with your classical ML,
Yeah,
and
exactly.
not even deep learning. That's the problem.
Hmm.
And like very famous professors like who are there in these field, there's always a fight between like discrete optimization people and continuous optimization people. To be honest, I've been with
Yeah,
people
yeah.
who do compete with each other on that, but a lot of good researchers in the recent papers have tried to merge these two things. They can't live apart, because again, ML and deep learning, they're all mathematical based. Eventually, you'll always need to find proper things. So you can pick up a lot of things from the discrete optimization. That's why this paper was important for me personally, because I found how you could bring up a discrete optimization task into a continuous optimization, merge it intelligently. This is how you do it. So this paper is very intuitive in that sense as well. So these are domain shattering papers, you have to keep in mind. So such papers are impactful papers, and such papers should be read actually. And it's an Indian author, so an Indian author, and from Bitsplan, if I'm not wrong. So that's a good thing. This is
No, yeah,
a
really. Like when everyone talks about machine learning and deep learning, that's always the differential functions that we talk about, right? So like this discrete mathematics is whole new field. Like I'm really thankful that you came up with this talk, because that's something new, to be very honest, for all of us, I guess. So yeah.
Thanks. Okay. So yeah, how? So I guess this was the last session for the day. I hope, like, I'll just make an announcement. Ashish, if you are there, you can, but otherwise I can do it. So, like, guys, like, tomorrow is like the last day for the symposium.
Yeah.
We have Ashish. He can continue the announcement, but yeah, like, do like amazing sessions are lined up. He is also going to speak.